This is practice midterm number 3, question number 2. And the question is, the combustion of ethanol is depicted by the following balanced equation. And I have C2H5OH plus 3O2 goes to give 2CO2 plus 3H2O. And part A is write the reaction using Lewis dot structures and make sure to use lines to depict the bonding pairs. And then part B is calculate the heat of combustion for 1 mole of ethanol using the following bond dissociation energies. And the bond actual enthalpies, the delta H for a carbon-carbon bond is 346 kilojoules per mole. The enthalpy, or delta H, for a carbon-hydrogen bond of dissociation is 411 kilojoules per mole. And delta H for a carbon-oxygen double bond, this is specific for carbon dioxide actually, is 799 kilojoules per mole. The enthalpy, or delta H, of dissociation of an oxygen-hydrogen bond is 459 kilojoules per mole. And the enthalpy of combustion, or enthalpy of dissociation, sorry, of a carbon-oxygen single bond is 358 kilojoules per mole. And lastly, the enthalpy of dissociation for a oxygen-oxygen double bond is 495 kilojoules per mole. So this is enough provided information to answer the question. And so we'll start with part A, which I will do on now. And that is going to be, I guess I'll use green for the reactants. We're not going to include molecular geometry in this case. We're just going to do the simple Lewis dot structures. And the reason for this is I want to illustrate which bonds exist, which bonds are being made and which bonds are being broken. And so this is ethanol, C2H123445OH plus oxygen, O2, where I have an oxygen double bonded to an oxygen, lone pairs included. It goes to, and this is going to be 3. There are 3 O2s. And it's going to give me 2 carbon dioxides. Plus 3 waters. So, once I have, the carbon dioxide molecule, I have a carbon double bonded to it. I have an oxygen double bonded to a carbon, which then is followed by a double bond to an oxygen. And 3 waters where I have a hydrogen single bonded to an oxygen, which is single bonded to another hydrogen. So this includes all the bonding information I'm going to need to answer question B. And so this is sufficient for your answer on question A, because there'll be a question like this on the test. Now, in order to understand the next part, where I have to calculate the heat of combustion for 1 mole of ethanol, I'm using the bond dissociation energies. We have to understand what goes into this. It's going to be, when a bond dissociation energy is going to be endothermic process. You have to put energy in order to dissociate the bond. And so I'm going to have, I want to just go draw a line through each of these bonds. All of these bonds are going to be broken. This is, since we're dealing with a path-independent function, a state function, I can do this. I can do it anyway. I'm not suggesting that this in fact happens in practice. This has nothing to do with what pathway is followed. This is a path-independent property. So I note the number of single bonds and the nature of the bonds, and I'm going to break all the bonds. It's going to be an endothermic. So this is going to have a positive sign. When the bonds are broken, I have to put energy in to break them, and I get energy back, or energy is released when these bonds and the products form. So now so I've depicted in blue to illustrate this. I have to put energy in, and I've done it in red. I get energy out. I don't know if there's any significance to blue and red. I just wanted a different color to represent which way the energy was going. So, and you don't need to draw these lines. I'm just drawing these lines to help illustrate. You could do this on scratch paper if you want to keep the books straight. So I'm going to have to add up all the energy that would go into breaking all of these bonds. And I'm going to have to subtract from that the energy that would be released when these bonds form. So now we can go to problem 2. Delta H for the process. I'll start out in black pen. Is going to be equal to, and I'll do in blue the energy that I'm going to be placing in. There is 1, 2, 3, 4, 5 carbon-hydrogen bonds that are going to be broken. So there is, I'm going to start out with, there's 1 mole of C2H5OH. And there is 1, 2, 3, 4, 5 moles of CH for every 1 mole of C2H5OH. Now that I've got, I can show that in my dimensional analysis. I need to include the energy that goes into breaking a CH bond. There's 411 kilojoules for every 1 mole of CH. And now I've got 1 mole of carbon bond. So I can actually place a bracket there, and for every mole of C2H5OH, I've got plus 1 mole of carbon-carbon bonds for every 1 mole of C2H5OH. And now I can take the energy from a carbon-carbon bond and include that, 346 kilojoules for every 1 mole of carbon-carbon bonds. And there is going to be plus 1 mole of, for every mole of ethanol, I've got 1 mole of carbon oxygen oxygen bonds for every 1 mole of ethanol. And that has a corresponding energy of 358. And we're almost done. The only remaining bond that we haven't discussed is the OH bond, plus, and there's 1 mole of O's. 1 mole of OH for every 1 mole of ethanol. And that carries with it an energy of, where is it? Oh, 459. And that takes care of my ethanol. Okay. Now I have to deal with the oxygen bond. I think I might be able to fit that on this line, plus three moles of O2 and 1 mole of oxygen double bond for every 1 mole of O2, and that carries a bond strength dissociation energy of 495 kilojoules for every 1 mole of O double bonds. And that takes care of all the bonds that I have to break, and I've depicted that in blue because this is all positive. And now I will depict in red what's happening on the other side. Minus, and then there's going to be 2 moles of carbon dioxide, CO2, and there is 2 moles of carbon oxygen double bond for every 1 mole of CO2, and 799 kilojoules for every 1 mole of carbon oxygen double bonds in CO2. That's the dissociation energy. It's different for different carbon oxygen double bonds, but specifically for carbon dioxide, it's 799 kilojoules. So I've taken care of that product, minus 3 moles of H2O, and there are 2 moles of OH bonds for every 1 mole of H2O, and there are 459 kilojoules for every 1 mole of OH. And now our dimensional analysis is clear. And this is really the most of the problem. In other words, if you include all this on your answer, you want to have all this detail, everything unambiguously assigned. Because now all we have to do is the trivial part, which is the calculation, which is somewhat a little bit tedious. We're going to have to do a little multiplication and division. But what I'm testing is this the setup. You have a clear setup. I don't care if you made a mathematical error. That's going to be a couple of points, but it's not going to be significant. The major point is your answer should include all of this detail. And this is clear. And so then we're going to be hunky-dory peachy keen. Now I'm going to have to go over to my scratch paper and do the calculation. And so I'm going to have to do on my scratch paper, which I'll go over here to this sideboard and do 5 times 400 and, well, I'll do it. 411 times 5, 5, 5, 4 times 5 is 20, 20, 55. I've got plus 346. Okay. So I've got 2055 plus 346 plus 358 plus 459. Okay, 6 and 5 is 11, 11 and 9 is 20, that'd be 28, 5, okay, 5, 10, 15, 19, 21, 3 and 2 is 5, 5 and 3 is 8, 8 and 4 is 12, that'd be 32, 18, 3,218 kilojoules, which is plus, and then do the calculation for the carbon dioxide. And then, but first let me check, did I get all of them? 459 and 495. Did I include 495? No, I did not. So I better go back and check that. That's why I want you to write this out, because of its it was 495, left out the oxygen, 495, which is a nice dyslexic event here. Yeah. What? And there's 3 of those. Oh, I have to calculate that. 495 times 3 moles. And so 5 times 3 is 15, 9 times 3 is 27, 28, 4 times 3 is 12, 14. So I'm going to have to add 1,485 to the total. Now do it one more time. Okay, 6 and 5 is 11, 28, and 5 is 33. Oh, okay, that's a different thing. 5, 10, 15, 4 and 3 is, okay, 4 and 3 is 7 and 8 is 15, 20, 25, 30. Okay, 3, 6, 9, 9 and 8 is 17, and that is 4703. Different number, but we've got that number for the endothermic process. Now let's do the same thing with the exothermic part, the bond formation. Okay, I have 2 moles of carbon dioxide, I have 2 moles of carbon-oxygen double bonds for every 1 mole of carbon dioxide, and 799 kilojoules. So that is 2 times 2 is 4 times 799. So I have 799 times 4. 9 times 4 is 36. 9 times 4 is 36. And 7 times 4 is 28. And 3 is 31. And then I'm going to have to do the same, almost the same thing. I have 3 moles of water and 2 moles of oxygen hydrogen bonds. So 3 times 2 is 6. 6 times 459. 459 times 6. 9 times 6 is 54. 5 times 6 is 30 plus 5. 4 times 6 is 24, and 3 is 27. So now I have to add 3196 and 2754. 6 and 4 is 10, 15, 9, and 3 and 2 is 5. So now I've got all the rough calculation on my scratch paper. I can go back and include this in. And so I will be putting the equal sign here, try to equals 4703 kilojoules per mole minus 5950. And that is equal to, go over to my scratch paper and do that operation. So I have 5950. 7, that would be 4, and it's 2, so that equals minus 1247. So the last part, the calculation, is a trivial part in terms of the number of points I'm going to ascribe, as long as you clearly have your setup, even if you make a mathematical error like you saw me make earlier when I failed to include one of these. If you have the setup, that's what I'm really looking for, but the last part includes it, and this is indeed an exothermic process, which you'd expect. And anybody who's ever held their hands up near a flame knows it's an exothermic process, combustion. Let's see if I can give an example of combustion in exothermic. See? Yeah, that's, if you put your hand in the flame, you'll understand. It's going to release energy. So you would expect that. That's indeed what we observe. And this would be the complete answer.